Yeah, well, it's about the same subject at least. So I put these numbers so as to refer to you some references. These are all papers of me and Tobias. And these two are more or less what Tobias talked about in his talk. And these ones, so this is Tobias' talk, so earlier today. These are some foundations, which will not be of interest to very many people in this room. And this is some further calculation that Tobias, with Tobias. But today I'm going to talk about these papers more or less, which are with my student Matthias Scharitzer. And I guess at some point I should give a title to the talk. Maybe the title can be Skein-valved cluster algebra. Okay, but that's the main topic of the talk. But before I get there, I want to emphasize a bit more something from Tobias' talk that I don't know how. Well, I just want to emphasize it a bit more because it's the one aspect of this story that I think some physicists might have some idea about what it means. So remember in Tobias' talk, and there'll be a similar thing happening today, at some moment we were, actually maybe this didn't appear in Tobias' talk. So let me, so remember there was some situation where you had some space. In Tobias's talk, it was C3. Okay, and then you had some Lagrangian. So this kind of Lagrangian, and then Tobias's talk, to do the calculation, he did this operation called stretching, and stretching means you choose some contact level set, and you degenerate the metric along this thing. So if you degenerate the metric, and so now you have something more like this. So this kind of okay, and then there's some discussion about we study. We originally begin life wanting to, in Tobias' talk, we began life wanting to count holomorphic, thinking about the moduli space of holomorphic curves which end at this Rabe chord rho, and then they come along this guy, and then they maybe do something in here, have some genus, whatever. And then the question was what happens to these things as you degenerate? And in Tobias' talk, the way he derived some recursion relation was that you wanted to know that they only break like this. Okay? And so what Tobias explained in his talk was that for a reason, and I want to discuss that reason in a second, for some reason, when you do this kind of degeneration, any such curve must break in this way. And if you think about it a bit more, I mean, also implicit in what he was saying is that all such possible, any kind of breaking like this, you can go back. And so the point is that I just review what he said, which is that he studied a one-dimensional moduli space of curves like this and took its boundary. This thing here was the picture of the boundary of the moduli space. of moduli, and hence it's supposed to count as 0. And what that 0 means is that so we'll discuss a bit. We'll discuss in a bit what that 0 means. But there was something which maybe glossed over slightly in Tobias's talk, which is why it is that this is the only kind of degeneration. Yeah, let me try again with what I'm saying. Yeah, okay, let me try again with what I'm saying. I'm going to draw the same picture, but the explanation of it's slightly different than what I said. Yeah, okay, so let me try again. You look at the boundary of this moduli space, and this moduli space, it has various kinds of boundary. It has the kind of boundary where you get a degeneration of the curve along the boundary, and as Tobias explained in his talk, that part canceled. But it has a different kind of boundary where some of the curve escapes to infinity. Okay, that's another possible boundary of this moduli space. And you can ask, what does it look like when some of this curve escapes to infinity? And that's the picture that I drew. So I draw that picture. It's the same picture, but its meaning is different. So what it looks like when some of this curve escapes to infinity is like this. So some part of this curve has escaped to infinity, so we draw it like this way, and some part of this curve remains in the finite space. Okay, are you happy now, Tobias? Yeah. Okay, so it's same picture, just I'd say slightly different words. But the part that was not emphasized in Tobias' talk is that there's a different thing a priori which could have happened here, which is that it could have happened that some. Let me just draw same picture. Okay, it could have happened a priori that. That you have some kind of curve here, which goes up here. It talks to some kind of curve here, and then this one continues like this. Maybe something non-trivial happening here also. Okay, in principle, when you do this kind of, when you study the boundary of this moduli space, this is something else which can happen. But the reason it did not happen in the case Tobias was studying, and it will also not happen in the case that I will be talking about mainly today, is that you can estimate the dimension of such contributions, and that dimension has to do with what's called the index of the Rabe chord. And in this geometry that Tobias was studying, as he said, there are upstairs here only Rabe chords of index 1. And so if when this goes up to a Rabe chord of index 1, then this moduli space will be one-dimensional, and then this moduli space it turns out negative one-dimensional. And anyway, so generically there's no such thing, and then this picture can't happen. Okay, so that's how in this business this morning this picture was ruled out. But the reason I mention this, I mean, also I'm going to be using the same argument, but the reason that I mention this is because I want to mention a different example, which was in this first paper of me and Tobias, which is this Oguri-Vafa example. And I want to mention it because there's a question I want to ask you guys. So that example is the following. You look at S3 and T star S3. And so T star S3 also looks like this. And you take, this time you have S3, the zero section. And you take a knot in S3 and you take its conormal and you stretch it out. You stretch it off somewhere else. So this is the perturbed not conormal, to some not. Okay, and I gave this, Tobias and I have been speaking about this now for like 5 years or something, so you may have seen this now many times, but when you count in this geometry, you get a single curve. And this single curve, you count it by however it meets this not conormal, which is some longitude of this not conormal tensor. However, it meets this S3, which is actually the knot itself. So this is the skein of the conormal, this is the skein of S3, and there's one such curve, so you count it by one. And then the way that Tobias and I in this first paper proved this Oguri-Vafa formula is we stretch here. And stretching here means that this new picture, it looks like this. Okay, and then you can ask same question. You can ask. So this is a bit different than this. Here we passed to the boundary of moduli space. Here we degenerated something. But so you can ask here. What do the curves look like in this limit? And the answer is similar. It's a priori somehow it could do many things. It could go like this. Maybe like just someone up here, down here, someone who comes all the way down here. Maybe just someone like this, okay? Just any such configuration could be in the limit. But in fact, so first of all, this person, it can't be there because the zero section is exact and the holomorphic curve cannot end. I mean, for Stokes formula reasons, can't be there. Okay, so not this one. And then by the same kind of index argument, for this configuration to exist, this Rabe chord, this Rabe orbit, it's called orbit now, has to have index 0. And the miracle of S3 is that it has no index 0 Rabe orbits. And this is more or less because the index of the Rabe orbits are more, within cotangent bundle, are more or less the same as geodesics. And you can calculate index of geodesic. In this case, you can see it has to be positive because it moves in a family. Well, anyway, there's no such thing. And it means there's none of this stuff. There's no place was ever allowed to break. So it's just the count upstairs. Okay, so just this thing. And so the count on this side was this, and the count on this side is a sum over all such curves. And I restrict attention to the ones that go once around this longitude, kind of longitude times its contribution, whatever. Okay, so it's a sum of curves, just like a sum of curves. And I mean, of course, I have to put this A to this kind of the four chain intersection, Z to this minor Euler characteristic. So it's a sum of curves, some kind of combinatorial factors. And the point is that, as Tobias explained in his talk, our count is deformation invariant. So as you do this deformation, it doesn't change, and you learn that these two things are equal. Okay, but that means this class of K in the skein of S3. Yes, sorry. I also have to say what the contribution is in this skein, but no one is here, so it's the empty knot. So this calculation tells you that the class of K in the skein of S3 equals the class of the empty knot times some curve count. So this is more or less this Oguri-Vafa statement. So the reason I mention it is because I wanted to ask a couple things. Yeah. What? This Taub's paper was basically nonsense. Taub's was trying to make some other Lagrangian. I mean, in Oguri-Vafa paper, they said something. Okay, they said this is some Lagrangian. Then Taub's was trying to guess what Lagrangian it was. I don't know if it was exactly this Lagrangian. It's wrong Lagrangian. Yeah, that's the wrong one. But I mean, the correct one is much simpler. You just take not conormal and you push it off. Yeah. But let me ask now my question, which the question is, in this kind of Guriev-Alpha paper or other physics language, they say some words about piling brains on here and creating black hole and going to like some geometric transition, maybe some near horizon limit, something. And my question for you is, I have two questions for you. One is, these Rabe orbits, so in our argument, it was absolutely crucial that no index zero Rabe orbits appear. There's a fact about the geometry that allowed this argument to work. And the question is, where is that in the physics? What does it correspond to? And to sharpen the question, there are other conifold transitions that people consider, which correspond to S3 mod some group. Okay, and for those conifold transitions, there are index zero Rabe orbits. And those Rabe orbits correspond to the fact, eventually, I mean, so when you run this argument, something more complicated happens, and those Rabe orbits correspond to the fact that for S3 mod finite group, Skein, I don't know if Tobias mentioned this, but Skein of S3, it's free module on the empty knot. And for S3 mod finite group, it's no longer true. And so this one still can make some argument for this conifold transition, but it's more complicated, and the fact that it works like this for S3 crucially involves this fact. There's none of this stuff. So it's a question for physicists where exactly in kind of physical account of this it appears. It still works, but somehow this kind of index zero Rabe orbit is a crucial aspect of the story. In this case, orbit. Here was chord, there was orbit. Here chord, here. I mean, here there's only orbits. There's no Lagrangian here, so there's still no Lagrangian. It's still the three manifold is here, conormal is here. Yeah. 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 So it's some. The mystery is for us is what is the name of these chords in the physics, and these orbits or the chords, and a related mystery, which may be more philosophical mystery, is that the move that is happening here or here, it has, I mean, certainly here, has to do with stretching the metric around this thing. And the question is, how precisely can you make that line up with this kind of black hole stuff and near horizon limits and whatever is happening in this ADS CFT? So that's maybe the final part of this mystery is if anything is correct about this being like black hole, the physicists say, if anything is correct, I mean, I don't understand what you guys say, okay, but if anything is correct about that, then this kind of business of connecting through a Rabe orbit is something that looks very mysterious in terms of things outside the black hole talk to things inside the black hole. So these are some mysteries for physicists. Yeah, no. So in the case that there was a Rabe orbit, so let's suppose something is correct about this statement, that this procedure is like some kind of black hole forming and splitting off. Okay, let's pretend that's correct. So if that's correct, then I mean that's consistent with this kind of picture because like the outside is not talking to the inside. Now, if, however, this was anything other than S3, then there would be these Rabe orbits, and then there is a way for the outside to talk to the inside by this kind of configuration I drew before. And so it sharpens my confusion about are we talking about black hole or not. This question for later. Let's discuss. This whole thing was some kind of, it has nothing to do with my talk. I just wanted to mention it. Yeah. No. That's for later. I posed the question. We can discuss it later. I want to give my actual talk. This part is this part. Yeah. Okay. So that was this kind of. If you are bored with the calculations I do now, you can contemplate these things. Okay. So what I actually wanted to talk about. Let me. So I've drawn up here this kind of skeins. And this is this Humphrey skein that Tobias was using mostly. And this is what's called U1 skein. It's a specialization of the Humphrey skein. As you see, this kind of equation here, it's a specialization. First you set some kind of like A equals Q to the 1/2. Z equals Q to the 1/2 minus Q to the minus 1/2. So first you make this specialization, and then you take some kind of further quotient to get this. And you see if you set these values of parameters, then this equation just turns into this. And certainly these two equations together imply this one. Okay, so it's some kind of and there's some kind of further quotient of this skein. All right. So let me something else which came up in Tobias' talk. Let me make it. Let me pause and discuss it a little bit, which is this quantum torus. So let's consider T2. That's going to T2 times R. Okay, we're going to consider the skein of this thing. And I'll draw a picture of this T2 times R. So this is the T2. And let's consider, for example, this element of this skein. Okay, so some element. If I use these skein relations, kind of equals this thing times Q to the 1/2. Okay, and this other one, if I do it the other way, equals the other way. Same thing. No, something is wrong here. Times Q to the minus 1/2. Okay, and skein of this T2 times R, or of anything times R, you can regard as an algebra, because you can put one copy of R next to the other copy and then smash them together. So if I call this element L and this element M, then what is written here shows you that if I first do M and then I do L, I do them from the top. First do M and then do L. Well, it's the same as first doing L and then doing M and then up to a Q. Okay, so that's why U1 skein of the torus is quantum torus. And if I have this kind of boundary of the torus, so in general, if M is a 3-manifold, then I can look at the skein of M, and it is acted on by the skein of the boundary of M. And the action, times R. Okay? And the action is just, like the boundary of M, if you stick a small tube on it, that's boundary of M times R, I can just feed knots in there, and they enter into here. And so in particular, there's an action of skein of T2 times R on skein of solid torus. And I want to compute this action. Well, what is it? Well, the solid torus is where the meridian becomes collapsible. And then I can use this circle equals 1 equation. And so if I have solid torus, well, I could have the, what are some elements of here? I could have the empty knot, okay? And I'm just going to declare that, so if I start adding longitudes, they just start piling up there. Okay, so I'm going to declare that this kind of this longitude, I act by it a bunch of times. I'm going to call the result x to the n. And then on the other hand, if I act by the meridian, well, first of all, if I act by the meridian on the empty knot, then the meridian becomes contractible in the solid torus. I contract it to 1, and I just get back the empty knot. But if I act by the meridian on x, well, this is the meridian applied to the longitude, applied to the empty knot, which is q times the longitude, meridian, empty knot, maybe it's q inverse something, q inverse, l, q inverse maybe, which is the meridian does nothing, the longitude puts it back to x, so q inverse x. Okay, so and more generally, if I put kind of x to the n here, it would pull out n copies of q inverse. So in other words, this calculation shows you that the solid torus, so this is the quantum torus, and I've calculated for you that this is its polynomial representation. Okay, and it's more generally true that if I put some other surface times r here, and I took the handle body, I would get polynomial representation of corresponding bigger quantum torus. All right, so that's just some kind of lesson about how to calculate. And the reason I wanted to explain this was, okay, I think we don't need this anymore. The reason I wanted to explain this was because of this equation that came up in this Tobias talk. With yeah, why not? Sure. I mean, the mapping class group acts on Skein, that's for sure. Okay, so what was I saying? Yeah, so the equation that came up in Tobias's talk is 1 minus m minus l. This I think maybe Tobias said it, but I say it again. So this if you ask, so this is in Skein. I mean, right now I'm having discussion at level view 1 Skein of T2 times R. And this picture from Tobias' talk, this kind of the picture that said that the count, there was a count that was supposed to be 0, and what exactly was that count? It was a count of stuff up here and down here, okay? And the count down here, it lives inside Skein of solid torus. And the count up here was this 1 minus m minus l or whatever. And so when Tobias said that something was 0, the thing that was 0 is this operator applied to this element under that action. Because that's what happens when you glue these back up. Okay, so that's the thing which was 0. And the reason why I want to mention this now is that this equation, it's a famous equation. This is the recursion relation for the quantum dilogarithm. Psi in Skein solid torus equals q dilogarithm. So it means that if I tell the story the way it should have been told up in the Homfley skein, then the true count of curves here I should regard as some kind of upgrade of the dilogarithm. Yes, yes. What? 1 minus m? No, the operator 1 minus m minus l was the count at infinity here. Because there were 3 curves. There were 3 curves. No, 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 no. No, no, this is C3. This is C3. Yeah, this is just from Tobias' talk. C3. Well, I mean, for now, same setup. This is just Tobias C3, Tobias operator. Tobias, let me give it a talk. C3, same operator. It kills this thing. Let me continue. So M is contractible in solid torus. Yeah, it's not contractible in here. But are you asking? So for example, suppose I study this operator, and I ask what solves this equation. Then 0 solves this equation. And any scalar solves this equation. This equation is different. Yeah. Okay. Yeah. Okay. So I continue now. So the point is that the solution, you should regard the solution to this equation in the true skein as upgrade of quantum dilogarithm whenever it appears. Okay, so that's some piece of the story. And the reason why that is interesting for this talk is that in this story about cluster algebra, what's called Q-cluster algebra or quantum cluster algebra is all about conjugation by the quantum dilogarithm. And so this story, it suggests that if I can make conjugation by this operator in the skein appear naturally, then I will have invented some kind of skein-valued cluster algebra. Okay, so that's the goal. The goal is to make appear conjugation by this element. And every time you do it, you somehow, yeah, so So now let me describe some kind of geometry in which this is going to happen. So the whole point of all this discussion so far was just to justify that whenever I see this kind of Tobias equation, then its solution is this kind of upgraded dilogarithm. So now let me discuss this new geometry. So this, yeah. So I'm going to discuss some kind of some Lagrangians and Legendrians that were introduced by Truman and Zaslow. I always forget how many N's and M's this guy has. Truman and Zaslow, and they describe the following thing. So they say begin with S2 and consider gamma in S2 a trivalent graph. And then they say, from this data, they're going to describe some Legendrian, lambda gamma, in the jet space of S2. And to explain what the description is, I have to tell you how to describe Legendrians. So what is jet space? Jet space is cotangent bundle times R. And I have to draw a surface in here. And the way you draw a surface in jet space is you draw a surface in as 2 times R, and the property of being Legendrian is just that the kind of cotangent vectors that that arise are like the derivative of the kind of the surface with respect to the R direction. Okay, it's called front projection. And so I'm going to describe to you this surface by describing to you its front projection. And the way it looks is the following. So you have this kind of trivalent graph in S2 times R. And I'm really not so good at drawing. But so this lives in some kind of plane, this kind of, and then this kind of R direction. And basically, over each face, there is kind of a region above the face and a region below. It's like a double cover. I mean, if you project down to S2, you get a double cover. And there's a region above each face and a region below each face, kind of like this. I would say there's two sheets above each face, and then they cross when you go across this kind of line. Does it make sense what I'm saying? I mean, the picture transverse to the line. Yeah, maybe the easiest way to describe this is I'm going to describe it. I'm going to draw you a picture of what it looks like on this circle times R. On this circle times R, it meets this kind of these spokes in 3 points, maybe here, here, and here, and it meets the surface like this. Okay? And you just kind of take the cone on this picture. And so by this construction, you build a surface, kind of an immersed surface in S2 times R, and then you lift it to a Legendrian in this jet space. And it's a fact, kind of ancient fact, that such a thing is smooth. This has to do with the fact it's trivalent. Yeah, some surface. Yeah. Anyway, it's some. Maybe this will help you. So it's projection at T star S2. It has some self-intersections, and the self-intersections, there's one of them sitting in each face. So in each face has a self-intersection. Okay. So I consider this guy. I mean, these people consider this thing, and the reason why it's a good idea, I mean, these people were led to consider this thing, is that in the symplectic geometry in general, we've learned a lesson that cluster algebra appears whenever in 2 dimensions you do something called Lagrangian or Legendrian disk surgery. And this disk surgery is some phenomenon where somehow some cycle collapses and expands in a different way. And in this kind of geometry, the virtue of it is that if you do a transition on the graph that looks like this, then turns out it's a disk surgery. Okay, so the virtue of this geometry is that some kind of playground where we have the symplectic geometric phenomena which are supposed to correspond to cluster transformation. So all right. Maybe I will. Yeah. So what this. So after Truman and Zaslow, I think Zaslow and his other collaborators, in particular Schrader, Shen, and Zaslow, they considered. So this I described to you a Legendrian in this jet 1 S2, which I can put inside S5, and then I can consider a filling into C3. And they constructed some fillings. And they constructed them by performing a similar kind of double cover construction in 3 dimensions. I won't describe it in detail because it's irrelevant to me for what I'm going to say now, actually what filling that you use. So I'll just draw the same picture from the beginning of the talk, but now with this more complicated surface. I think that's probably correct. I think that's probably correct. So the place. So the place where you. So I want to discuss the quantum cluster algebra, but you're asking what is the corresponding classical cluster algebra, and what these guys prove is that if you look at the mirrors to these lambda gamma, that the mirrors to the mirrors to the pair. So you can look at C3 lambda gamma, okay, and it mirrors some kind of curve. It's not a curve; it's higher dimensional. It mirrors something, and the mirrors of all these different guys, they can be patched together along cluster transformations. Yeah, the mirrors themselves can be patched together. I can explain to you why that is, but maybe not now. I'll discuss later why that is. I mean, not in this talk. I can explain. Okay, so uh, yeah, but I don't want to talk about mirror symmetry now. I want to talk about quantum cluster algebra. But yes, mirror in the sense of, I mean, strictly speaking, mirror in the sense of moduli space for augmentations for DGA. Yeah, but yeah, all Lagrangian fillings. Okay, so what did I want to explain? Yes, I want to explain about how do you see this conjugation by this thing. But I was saying that Schrader, Shed, and Zaslow, they constructed some fillings of this lambda gamma. And these fillings, they have the same kind of miraculous property that this kind of Aganagic Waffe brane does, which is they have no index zero Rabe chords. So, sorry, lambda gamma itself has no index zero Rabe chords. So I can play the same game. Lambda gamma here, and some filling. And if I want to, so some filling, I'm gonna call it L gamma, although the filling doesn't only depend on gamma, it depends on some other data. So some filling, and I can ask, count curves. So this is the question Schrader, Shed, and Zaslow were interested in. They wanted to count curves on L gamma. And let me mention that unlike this kind of Aganagic Waffe brane or any of this toric stuff, there is no chance anyone has ever in the past been able to do this calculation. Because you can't do it in algebraic geometry, you can't do localization, somehow So they wanted to count these curves. And they made some conjecture about how to do it. And with Matthias, we proved their conjecture. And the proof was this kind of thing that Tobias was explaining. So the proof, I just draw, it's the same pictures as before. Somehow okay, I don't draw this one yet. We count curves. We count curves asymptotic to some Rabe chord. Index 1, the moduli space like this. We study its boundary. Its boundary, because there are no index 0 Rabe chords and no index 0 Rabe orbits, its boundary looks the same as this picture that I keep drawing. It has some stuff upstairs and some stuff downstairs. Like this, okay? And what we learned from this, to count these curves, instead, count curves for this lambda gamma times r. And that's this count. I'm going to call this count A rho. And I'm going to call this count psi gamma. And what we learn by the same argument that Tobias explained is that A rho A rho times psi gamma equals 0. And what is the meaning of this equation? Well, A rho, it's an element of this skein of lambda gamma times r. Remember, lambda gamma was a surface. And this thing is an element in the skein of L gamma. And so it makes sense to multiply them because the boundary of L gamma is lambda gamma. And the statement is that because there's no index 0 Reb choroids, product is 0. And so what Matthias and I do is, in our first paper, is we compute this A rho explicitly and show that it matches whatever Schrader, Shende, and Zaslow conjectured. It's somehow a long story how they conjectured what they conjectured, but so we just compute it. But that, yeah, so that's why. So the point is, so how do we compute it? We compute it using Tobias' method of flow trees. So as I said to you, there's one kind of Rabe chord. So what are the Rabe chords? Basically one interesting one in each face. And Tobias' flow tree method tells you more or less that the disks ending on this Rabe chord somehow limit to these things. And that's A rho. A rho is the count of these disks. That's it. Now, but that's not what I wanted to explain here. So you can write the formula explicitly. What Schrader, Shende, and Zaslow more or less show in their paper is that once you prove this formula that they conjecture, it uniquely determines psi gamma at least in the U1 skein. That's what they prove in their paper. But that's not what I wanted to explain now. What I want to explain now it's non-trivial fact. They spend like 30 pages proving it. I just told you they spent 30 pages. Oh, I mean, yeah, sorry. It's not unique. I mean, it's a unique solution that begins with 1 plus something and lives in some particular completion. Yeah, so under some condition, it's unique. But the proof is not trivial. So in this case, in this case, all the homology can be read off the skein element. So there's no need to keep track of it. Okay. So but that's not what I wanted to explain. What I wanted to explain is where do you see the cluster transformation? Because we haven't seen it yet. And where should we see it? We should see it in the relationship between the kind of A rows for this guy and the A rows for this guy. Okay, so I should explain to you where it comes from. And to do that, I need to explain to you one last piece of geometry, which is what is this disk surgery I mentioned, or like how are the Legendrians, which correspond to these graphs, related? So let me explain that. Okay, so as I explained to you already, the way the way to learn about Legendrians and study their geometry is you draw these pictures in this front projection. So I'm going to draw for you some front projection of what this kind of transition between these two surfaces looks like. And it won't be obvious that it's this. I mean, one has to do some, but I'll just draw for you what it's supposed to look like. And it looks like this. So this is the before picture. So before. And this is the after picture. After. And I'm supposed to draw for you a surface. So this doesn't look like a surface, but what you should do is you just spin it around in a circle. And then it's a picture of a surface in 3 dimensions. Okay, and then you kind of you kind of lift it wherever, and then this thing I call disk surgery has to do. It's called disk surgery because if you spin it around, it's a disk. Okay, so that's the before and after picture, and I want to describe that. I'm going to give you a cobordism. Here I've just described before and after, but if I want to prove some relation, I should somehow, within symplectic geometry, I should relate them. And the way you do that is you make a cobordism, and let me draw you how to make the cobordism. So the before picture looks like this, and I'm going to add onto it this guy. And I think this showed up in Tobias' talk, this picture. Did you draw this one? Yeah. This is this picture of this boundary at infinity of this Aganagic-Waffe object. Okay, so I put this one here, and then I do some kind of a handle attachment here. So this is the before. This is the beginning. And then I do some kind of in the middle. It looks kind of like this. Yeah, for the physicists, this like some kind of cultural experience. Okay, there's not how much you can learn from this, I'm not sure, but there's the middle, and then this. I guess this is the end. So this is the beginning, and this is the end. And what happened is I did some kind of handle attachment to these points. If in 3 dimensions, I've kind of filled in some annulus. But let me draw now what this there's kind of a movie of this thing, and this cobordism. So it ends up looking like, so this is the beginning. I call it lambda minus, and I call this n lambda plus. And lambda minus looks like this. There's some kind of lambda sigma minus, and then this kind of T2. This is the same T2 appeared in Tobias' talk, and then it's kind of lambda plus. Okay, that's the cobordism. And then to understand how the I'm going to now count curves in this geometry. So this whole thing, this whole cobordism, it lives inside an S5 times R. And yeah, so I can count curves in this geometry. And in fact, what I'll do is I will study the same kind of thing we were studying before, which is I fix a Rabe chord here, this kind of row of index 1, and I study the kind of one-dimensional moduli space of curves ending here. And I study its boundary. And what you discover is that its boundary, the kind of things which can happen in its boundary, it kind of looks like yeah. There's many, but I pick one. Yeah, I pick one. Yeah, there's lots, but I pick one of them in particular. Yeah, finitely many. There's some finite amount of Rabe chord, and I pick one. And I study the moduli space of like one-dimensional. Yeah, one for each face of the graph, and I pick one. Okay, so, and then I study what happens. And again, the way this moduli space, this one-dimensional moduli space, its boundaries, well, there's kind of where the curve itself degenerates, so it's all canceled by the skein. And then there are like 3 kind of places to which something interesting can escape. So the kind of one kind of interesting thing that can happen is like this. Another kind of interesting thing that can happen is like this. Actually, these are the interesting things that can happen. Either some stuff can escape out the top, or it can escape out the bottom. And if it escapes out the top, then like I have here this kind of count here, which was A rho plus, or minus, plus. And if it escapes to this part, I have some A rho minus. And if it escapes to this part, I have yeah, if it escapes to this part, I have the operator that Tobias described. There's 1 plus L plus M, and maybe minus. Okay, that because we already computed it. That's what happens here. And so, okay, so now what I do is I fill in this thing. I fill in this thing, and there I put yeah, sorry, I should have drawn this differently. I should have drawn it like this. Some stuff can escape here, and maybe I'll draw it like this. Because yeah, sorry, I'll draw it like this. Like it's really like this. It's really like this. I mean, something can escape out any place, right? So yeah, it can be yeah dimension, yeah. Yeah, that's right. Yeah, that's right. Uh, uh, we have to prove something, and what we have to prove has to do with this and this. And what we have to prove is that in these degenerations, the only thing that happens here is kind of a trivial strip. Sorry, it can be a trivial strip like this, and here it can be a trivial strip. That's fine, and anything going here. Okay, you can do anything at all here, but if it's in this part, it has to be trivial strip. Actually, sorry, if there's no one continuing here, there's none of this. So this can be anything, and this has to be trivial. That's what we have. That's what we prove. Okay, and then so that takes a proof. I'm not going to explain it, but then you do the following thing. You plug in this cap and you put in psi here. And I put it also here. And I put it also here. And the virtue of this is that because of what happened in Tobias' talk, it doesn't matter what's going down here, this part is 0. And so because the way this breaks, I have whatever, and then I have the operator from Tobias' talk, which annihilates psi. So it's like 0 because it's 0. And so what I learn is, okay, and now I suck this psi back into this kind of cylinder where it belongs, and I learn that this picture means, well, let's read it from the bottom, that psi a rho plus, and let's read this one also from the bottom, equals a rho minus psi. And that is Skein-valved cluster transformation. So I guess that's a good place to stop as any. Yeah, I mean the psi is the thing that is this kind of. I mean, So I could have said something slightly different, which is that I don't stretch this one all the way out, but I keep some kind of non-exact Lagrangian here. And then there'll be some actual contribution. That turns out to be technically annoying. So I don't want to regard this psi as an actual count. I just attach it formally. But you could view it as somehow I had taken non. I mean, here I had some technical point of this discussion is that here I've made an exact cubordism from lambda plus to lambda minus and this T2. If I were to plug something actually geometric in here, I'd have a non-exact cubordism, and there's some annoyances that we didn't figure out how to deal with that. So for this reason, I do not regard psi as an actual count of something, at least technically in this argument. But there should be some version of this argument where I take non-exact cubordism and it's just a count. But I mean, what it is, it's the count. Maybe Tobias was saying it's the count he was counting this morning. It's that count. I agree that's true. I don't know. I don't know any meaning of that coincidence. I've also never understood that picture precisely. I know that people draw that picture. I don't know what it means. No, I know what philosophically it means. Is that literally true, that that's literally what happens in the moment map, or they just like to draw it? I see, okay. I see. So, how to say it? There's no chance I can answer your question because I already, at the beginning of your question, there was an interesting question about what do these trivalent graphs have to do with toric geometry? And I don't know the answer already to that question. But maybe probably something interesting, but I don't know what it is. Yes. Yeah, yeah. I mean, in particular, in U1 Skein, it just is the quantum Bell logarithm. Well, maybe I just used the wrong symbol. I mean, it's wave function here, but somehow. Are you asking a philosophical question or technical question? I mean, maybe the answer to you is the following thing. So here, psi is being like wave function, okay? But here, the operator which annihilates it is not happening, and it gets kind of. I have a cubordism here. So this picture is not an algebra because it has like one input and two outputs. But once I cap it off here and kind of feed it back into here, now it's an element of an algebra again. So then, I mean, when I write this psi, it really means that there was the longitude here, and really what I should have written is that there's a longitude of this torus. That longitude, when I suck it in here, it becomes something like this, and I put psi on that knot. Yeah. Does it make sense now? Okay. Okay. Yeah, you can keep going. Yeah, I mean, you can compose this equation as much as. I mean, nothing. I'm not sure what you mean. Nothing commutes here. I mean, this Skein algebra is not commutative. This is a product of the Skein algebra of this. Of this surface. Yeah. So of course, if they're not adjacent, then it commutes. But if they are adjacent, then no. Well, I don't know. I mean, let's see. Okay, so if I shrink first this edge, I should draw two copies of this graph. Okay, so here's one copy, and here's another copy. Okay, so I'm gonna shrink this first, this edge, and then this one. Okay, so I shrink first this one, and then this one. Okay, so I wind up with this. And now let's do it the other way. I shrink first this one, and then this one. What am I doing? No, other way around. So it's just different graph. Yes, so for example, you could ask, can you derive a Skein version of pentagon relation? And the answer is yes. So in the original paper with me and Matthias, we did not succeed in doing this. And so some other people succeeded in doing it in other ways. So one of Tobias' student has proof just by hand of Skein-valued pentagon relation. A student of Zaslow has a proof that kind of uses our paper and then does some by hand stuff. But what you would really like is to see it directly from this, and we can. But by now we can also do that. But it's not currently. I mean, at some point we'll update the paper, put it. But somehow it's not. Yeah, but it is possible. So there's kind of if you do the sequence of graph mutations, which encodes pentagon relation, you can use that to prove a Skein-valued pentagon. Say again. Yeah. Yes. 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 So you were asking. Yeah. Okay. So you were asking. I didn't decorate this by some row. So yeah, I should have decorated this by a row, also this by a row. They both carry a row, and part of this thing is that there's a bijection between these Rabe chords. So well, I mean, you can see why there's a bijection, right? Like when I do this move. So if you believe me that Rabe chords are about faces, of course these are the same faces. There's bijection of faces, and so that bijection gives you bijection of Rabe chords. And the one contentful, the one thing we have to prove in this argument is that when you do the curve count in this geometry, then the only things here are trivial strips from the corresponding Rabe chords. That's the from the point of view of symplectic geometry, that was the one theorem in this. Yeah. I have no opinion about this question. Yeah, sure. I mean, no. Are you talking about this kind of abelianization? Yeah. So that's a different story, but it also exists. Yes, it also exists. But this I explained in 1 minute at string math.